Okay, done. Now that's unmuted.
Very good. So yes, Piotr is going to tell us about, can we go back to the first?
Yep, we can go back to the first slide. Yep.
The relation morphisms of directed graphs. Piotr, please.
Thank you very much, Rusbek. For starters, a big fat thank you to Rusbek for orchestrating our visit here. There is a Polish invasion of 4 people here in Sydney, and to Elizabeth for taking such a good care of us. So thank you, hosts. All right. So without any further ado, let me go to my topic. I have only 45 minutes, so I have to be brief. You see, Mateusz defined path algebras. Elizabeth defined Leavitt path algebras. I'm going to go one step further and define graph system algebras. And they are very beautiful in the area of sister algebras. They are nuclear, they're constructed combinatorially, and they are really important both in non-commutative topology. This is where we come from, at least I and Tomek. But they're also very pivotal in the classification of sister algebras. This is where Soren comes from. If you remember the spectacular success of the Elios program of the classification of the NUS algebra, so nuclear unitary, simple, and I forgot what the 4th S was for. It's been complete, but they are simple sister algebras. They have no ideals. And the biggest chance to move with the classification program beyond simple sister algebras is precisely going to graph sister algebras. And this is the area where Soren is working on. So we have these 2 big motivations. And one of the reasons why we are so much in love with the graph sister algebras is because K-theory is given to you on the plate. You can read it out of the combinatorics of a graph. You just construct a simple Z matrix from some Zn to some Zm, and you compute kernel and co-kernel, and that's it. You have both K1 and K0. So K1 is the kernel. That's why there's no torsion. Yeah, because you go from a free group. So any subgroup of a free group is a free group. So there's no torsion. And then you go to co-kernel. Then you can get many things you want. So although admittedly the class of graph sister algebras is very thin, very narrow, even among nuclear sister algebras, but it is very exciting, very fascinating because of this hands-on approach that you can exercise. And there are many generalizations, as I wrote here. You have higher rank graphs, so basically you add colors to your edges. You have quantum graphs, so basically you take the adjacency matrix of your graph and you say, no, these guys are not numbers, they're operators. And you have topological graphs, and this is actually very exciting. You see, you have your space of vertices, you have your space of edges, but why not topologize it? Why do we stick to discrete topology when we can be locally compact Hausdorff, right? And indeed, people did it. And for instance, our theory of contravariant induction works perfectly well in the area of topological graphs, and it was done by Katsura before we did our discrete part. And I can tell you that there are some things that are not possible to be done in the realm of the usual discrete graphs, but my student did it using topological graphs. And I'm very proud of him because he was thinking out of the box. He solved his problem by developing new tools. So I'm really happy about it. And that's precisely the way he did it, is by using topological graphs. Okay. Now, what we are in particular interested in, by we, I mean my collaborators and myself, that we don't want to look at these graph sister algebras statically. We are interested in the dynamics of graph sister algebras, which means morphisms between them, okay? And just as, you know, the graph sister algebras to us are given combinatorially, we are looking at this special morphism that can also be given combinatorially. And here's a picture I always like drawing to tell you about something I'm sure you know about. Imagine that you have 2 finite groups, finite just for the sake of simplicity. And imagine that you have a group homomorphism in the kindergarten. And now you can have obviously 2 functors, one covariant and one contravariant. You can take the group ring, it's a nice group algebra, and you have a covariant algebra homomorphism from Kg to Kh. But you can just take also all maps from H to K and all maps from G to K. These are also Hopf algebras in the obvious way. And now we have a pullback, the contravariant functor, right? So this is what we experience. We have we have graph system algebra. So here for graph system algebras, at least these objects are always the same. The construction is the same. But having a morphism of graphs, we can induce star homomorphisms both way, covariantly and contravariantly. And these are completely different constructions. However, what happens in the real life of examples, it turns out that we have to use both covariant and contravariant constructors à la fois. And this prompted us to look for a common denominator, to look for a new category of graphs which would subsume the other two categories, and we looked into constructing one functor where to simultaneously subsume both the covariant and contravariant functors. So that's what my talk is all about. So that's what we want to unravel. We want to have some nice category of graphs. I have a morphism from my graph F to my graph E, and it functorially induces a star homomorphism from the sister algebra of E to the sister algebra of F. Okay, but now let me give you even deeper motivation of why we were so desperate for finding this one functor and one category of graphs. It comes from non-commutative topology. Here I give you a very nice example of a push-out. You get a two-sphere by shrinking the boundary circle of the disk into a point. Okay, so this is the left push-out diagram. And then you apply the Gelfand functor of taking all continuous complex valued functions, and you immediately turn this push-out into a pullback. Okay, this is immediate. Everything is fine. It's a functor which changes push-outs into pullbacks, and we very much would like to have the same situation for graphs and graph sister algebras. We would like our graphs to be like quantum spaces. Then we apply a contravariant functor and have a pullback of graph sister algebras. But that's not so easy. And now if you do the non-commutative version of this nice push-out and pullback diagram, well, first you have the pullback diagram because, in non-commutative geometry and topology, sister algebras come first. Spaces are kind of come secondary, and they are just objects that intended as things that help you to think about it, but when you compute or prove, you actually work really with sister algebras. Okay. However, here, behind these sister algebras, we really have something concrete, not just abstract dual category that tells you nothing, but you have graphs with the combinatorics. So if you take, say, the definition of a Leavitt path algebra and you apply it just to this one loop, then you get Laurent polynomials. If you complete it in the sister norm, continuous function of the circle. Now, this gives you the Teplitz sister algebra, or if you want the sister algebra of continuous functions on the quantum disk. This is a celebrated Teplitz graph. If you want, this is the sister algebra generated by one isometry, the universal sister algebra. Or if you want to be concrete, you just go into L2N Hilbert space and take a unilateral shift, and you generate a sister algebra inside the B of H. Okay. Well, this is very simple. If you have just a one-point graph, the Leavitt path algebra, graph sister algebra, path algebra, whatever, it will be just complex numbers, or your field, the ground field. Well, it's a bit non-obvious, but if you take countably infinitely many edges going from the left vertex to the right vertex, well, this is nothing but the minimal unitization of compact operators, which is also interpreted from the quantum group point of view as the Podlesh quantum sphere. So if you want, this is exactly the non-commutative version of these two commutative diagrams. But you see, here this diagram sucks big time, because these arrows are not aligned properly, you see? These two arrows go in the right direction, and if you want, these are just admissible subgraphs, incorrectly called in the literature quotient graphs. And you apply the usual thingy, you just kill the missing vertex, and you kill all arrows ending in the missing vertex, and this gives you a surjection of graph sister algebras or Leavitt path algebras. Much in the same way here. You just kill the missing vertex, and you kill the edge which ends there, and this gives you a quotient map, which in terms of the usual sister algebraic generators, you just turn the isometry that you have here into the unitary over there, right? That's the famous symbol map, which is in every textbook on sister algebras, okay? But now, when you want to understand actually this star homomorphism, all right, Then, in terms of generators, it goes this way. You take your first edge. This is some partial isometry, and you map it to that edge, which is another partial isometry. But now you take the second edge, and you map it to a path, a circle followed by this edge. So this is the partial isometry assigned to this path, or if you want, the multiplication of two partial isometries, and so on and so forth. I mean, you basically compensate the infinity that you have here in terms of edges by the infinity of possible winding numbers. Okay, and this is how we get the map, and this is what induces a star homomorphism, but it induces it covariantly. Well, and here it's just the inclusion of this is the unit map of complex numbers into a unitary algebra. And for us, it was very frustrating because we have a very general mixed pullback theorem, okay? And this mixed pullback theorem actually encompasses so many important examples coming from non-commutative topology that it is precious to us. But on the other hand, it really sucks big time when it comes to conceptual understanding, because how can I apply two different functors to one diagram? It's completely frustrating. Okay, so we were desperate to find a category, one category and one functor in which we would reverse these arrows. Okay, and then we'd have one contravariant functor turning this commutative diagram into this diagram over here. Okay, so that's the goal of my talk, to show you this one functor to rule them all. But first, let me remind you this basic concept of morphisms. I was alluding to it when I piggybacked on Elizabeth's talk. But to be on the same page, I want to make sure that you understand it. Homomorphism or a morphism of graphs is something very simple. You map edges to edges, vertices to vertices, and the end points and the start points have to be respected. Okay. Now you go a step further, and you define the path homomorphism of graphs. And now this is just a map from finite paths in E to finite paths in F. And you demand that the following three things are satisfied. You map vertices to vertices. Of course, you must preserve start points and end points. And you also respect the concatenation. So if your paths P and Q can be concatenated, then F of such a path must be equal to F of P concatenated with F of Q, and you know that they can be concatenated by the condition to above. And this is an immediate exercise that if on the top of it you put the fourth condition, that F respects the length of a path, then you land back in here. Okay. In any case, because of the third property, you immediately know what is your F on any path if you know it on any edge. Okay. All right, and now this is our piece of notation, OG for ordinary graph homomorphisms and PG for path homomorphisms of graphs. And well, that's this step I wanted to show you. Now we define a new category. We still have graphs as objects, arbitrary graphs. I do not discriminate among any graphs. So you can have not only infinite emitters, you can have uncountably many edges emitted, okay? It can go into any infinity you want, okay? And this is what Ranga did in Colorado Springs with the Nymark's problem, okay? All right, and now just like in set theory, what happens when I have a map from X to Y and I have a map from Y to X, but I want to have them both at the same time. So what do I do? Well, I say, let's define a relation, which is A subset in X cross Y. And then I can have both these morphisms as a special case of a relation. I take graph of one map, I take the graph of the other map. Okay? So that's the basic idea. And here we have the following demands. Well, the condition number one basically tells us that the relation preimage of a vertex must be a vertex. So in other words, you cannot have something longer than a vertex in a relation with a vertex. And the other one is obvious. If X and Y are in the relation, then the beginnings are in the relation and the ends are in the relation. And this gives us the ambient category. And in particular, if you want to have a graph homomorphism as a graph relation, well, then this is the relation. If you want to have a path homomorphism of graphs as a relation, well, that's the relation. And note that this is exactly what we do. We invert the direction of this path homomorphism of graphs, because the relation that we assign to a path homomorphism of graphs goes into the opposite direction, which is what we want, if you remember the diagram before. Okay, now this is a definition that I refuse to repeat because Elizabeth did it, and you surely remember it. It's just, the notation. But I want to deliver on my promise and define the graph sister algebra. So for starters, let me consider the usual sister algebras over complex numbers. So my ground field is now C. And, if I want to have a sister algebra, I better have a star algebra first. So these ghost edges that Elizabeth introduced were done for the reason. The reason was to have a star structure. Okay, that was the clandestine reason, which she didn't reveal to us. So it was without spoilers, but the real reason why you wanted is to introduce a star structure. And the star structure is pretty obvious because we don't double our vertices, so vertices are self-adjoint. But as you can imagine, we map edges to ghost edges, and we map ghost edges back to the edges. All right, and you can quickly check that these formulas render both a path algebra of extended, or as you call it, double graph, and the Leavitt path algebra. They turn them into star algebras. Okay, at the moment you have a star algebra, you can ask yourself the question: can I define the universal sister algebra of the star algebra? Forget about path algebra. This will not give you anything. You'll not have any nice sister algebra here. But when you come to the star algebra of the Leavitt path algebra, so we have the Leavitt path algebra over C with the fast defined star structure, then in fact these are very, very nice generators because they are either projections or partial isometries. So they are very bounded. They are very, very bounded. So not only the universal sister algebra exists, but it has very regular properties. You see, in general, when you take the enveloping sister algebra of a star algebra, you are not guaranteed that your star algebra you started with is a subalgebra of your universal sister algebra completion. Because if you have nilpotent self-adjoint elements in your algebra, which you might have on the star algebra level, then they must die in the sister algebra. So first you take your star algebra and divide it by a certain ideal, okay, which need not be zero, so that you kill such unwanted guys, and only then you complete. But here you don't have to do it. LCE, the Leavitt path algebra of E, is a subalgebra of a graph sister algebra sister of E. And so it's a little bit like with amenable groups where you have that the reduced sister algebra and the maximum sister algebra coincide. Okay. Now, let's consider some subcategories. I already introduced you to ordinary graph category and to path graph category. And as I told you, if you take a path homomorphism that is length preserving, then you have the ordinary graph homomorphism, right? But now, in order to have respectively covariant and contravariant functors, I have to put completely different conditions for contravariant induction and completely different condition for covariant induction. So here there are no longer any relationships, there are no longer any arrows between them. Okay, and if you want to go contravariant, let me do it in two steps. So if you just want to induce a homomorphism between path algebras, then all that you require is that your graph homomorphisms are proper, which in discrete topology means finite to one. And if you want to go further, if you want to respect Cuntz-Krieger relations, you need target bijectivity, which I'm not going to explain now, to preserve a first Cuntz-Krieger relation, and you need what I call contravariant regularity to preserve a second Cuntz-Krieger. And then when you have it preserved, well, the same formula actually defines you a star homomorphism between graph sister algebras, or if you are algebraically minded, just a homomorphism between Leavitt path algebras. You see, it's very important that if you define graph sister algebras this way, and that's not the usual way they are defined, okay, this is why I'm defending this point of view. Typically, graph sister algebras are defined in a different way, but I believe that this path algebraic way is the cleanest one, the most useful one. You see immediately, right away, because of the universality property that if I have a morphism between Levi-Pav algebras, I automatically always have a morphism between graph system algebras. So if I have a functor into Levi, I have a functor into graph system algebras. However, you have to be careful with pullbacks, because taking pullbacks does not commute with taking completions. Okay, so you might have a pullback of some dense subalgebras, and then if you complete this, if you complete the pullback algebra, it need not be the same as the pullback of a completed algebras. So that's a bit subtle with doing pullback theorems for Levi and for graph system algebras, but we are not getting there in this talk. Okay. And now for the covariant functors, well, to have a homomorphism between path algebras, all that you need is that you are injective on vertices, which is kind of obvious, because as Elizabeth explained, vertices are mutually orthogonal projections, and you cannot fuse mutual orthogonal projections because you get a contradiction. Remember that vertices are not zero. In fact, you showed this Goodrell's theorem that you can embed the whole path algebra in the Levi-Pav algebra, which means that all generators are non-zero, they are parts of a basis, so you cannot kill them. Okay, but this is a very mild condition. Now, if you want to have covariantly induced star homomorphism between graph system algebras, you have to have monotonicity conditions, I'm not going to explain, and a really daunting regularity condition, which again, I'm not going to explain. If you have them done, well, then you are guaranteed that you have a functor into sister algebras, and a path homomorphism of graphs which satisfies these three conditions will functorially, covariantly induce a star homomorphism between graph sister algebras. But maybe since we are talking about gradings, well, instead of gradings in the lingo of of a native tongue, right, of graph sister algebras, we say about gauge action and gauge equivariance. Just remember that the Pontryagin dual of a circle is Z. So to say that your space is enjoys a U1 action or that it's Z-graded is the same thing. Okay. So in Leibniz you say Z-graded because when you have an arbitrary field, it's hard to say that you have a circle. But when you have complex numbers, it's really completely equivalent to say I'm Z-graded or I have a gauge action. Okay. And the gauge action is very simple. You do nothing with vertices, and every partial isometry associated to an edge is rephased by the same unitary complex number. Okay. All right. Good. And oops, now there's a commercial break. Sorry. By law, I have to flash that you. So we are all four of us. We are funded by the European Union and the Polish government. And Western Sydney University, which is here in the red, right at the bottom, because it is our latest acquisition. We have this graph algebras program, which is a 4-year program involving about 80 mathematicians from 26 places, and out of 86 of us are here. Okay, can compute the percentage, and this is our whole network. And our visit here of the four of us is part of this program. Okay, so the sponsor was acknowledged.
In your mouth.
Oh, we love graph algebras. Yes. Yeah, we climbed the bridge to sing "We Love Graph Algebras," for that reason. Okay, and now that's like the slide. So now I'm going to go very slowly. My apologies to Tomek, who is hearing it 100th time, but for you guys, that's new. So this is the takeaway, right? So you see, because here, all these conditions are different, please don't be surprised that I want to bundle them up in one place. I have to have them kind of separate, right? So this is why I have to have so many more conditions, because I have to simultaneously take care of a covariant and contravariant functoriality. Okay, for starters, we have a very benign condition, multiplicativity. This is, Tomek, what you asked me at lunch. But it just says that if I have two pairs of paths that are in the relation, okay. I have two pairs of paths that are in the relation, and if x and x prime can be concatenated, y and y prime can be concatenated, then the concatenations are also, in the relation, okay? That's clear, right? Next, going the other way around, decomposability. But mind you, here things are not symmetric. Right and left play distinctively different roles, all right? So decomposability happens only on the right-hand side, because the right-hand side is kind of like the domain of my covariant functor, which does not preserve the length of paths, okay? And okay, so what happens there? What happens there is the following. If you have a pair of paths in your relation, and if you can decompose this path into y prime, all right, then it means that you can also decompose this x bar into paths x prime such that x is in the relation with y and x prime is in the relation with y prime, okay? If you can decompose, then you can decompose on the, if you can decompose on the right, then you can decompose on the left and match everything. So it's like the reverse procedure. Here I have differentiation, here I have integration. Okay, you can always do it in the trivial way. If y or y prime are vertices, right? Then it's obvious. You can always do it. But here the whole case is that if y and y prime are edges or some longer paths, yeah, then you can decompose x bar into appropriate paths such that these parts coming from the decomposition of x bar will match appropriate parts of the decomposition of the right-hand side, which is y and y prime respectively. Okay. Now, properness, that's very easy to say. I take the relation preimage, so I take all guys on the left that are in the relation with one single guy on the right, and I want them to be finite, okay? I cannot have infinitely many paths in a relationship with one path on the right. That's forbidden. But the other way around is allowed. I can have, if I would take here the relation image, so I can take a path on the left, and this path on the left can be in relation with infinitely many paths on the right. That's quite all right, but not the other way around. Now, that's the most tricky one to explain. We call it a partial vertex function, because by what I just told you, the image can be infinite, all right? Not only more than one, it can be infinite. And in fact, in very simple examples, I can have a graph which is just one point, and I can have a graph which is just one loop, okay? And basically, the relation is that this vertex V is in a relation with all powers of this loop n, and the zeroth power is the vertex itself. So you see V and Un, where n runs natural numbers, including 0, are in the relation. It's okay. But if I restrict the image to vertices, okay, then a vertex can be in a relation with at most one vertex. It can be in relation with nothing. I mean, there can be a vertex which is not related to anything. But if it is related to a vertex, it's only one. Okay? Can be related to infinitely many paths, but only to one vertex. At most, one vertex. Okay, now here's the target bijectivity condition, which is basically taken like verbatim from the covariant property. That's to satisfy the first Kuntz-Krüger relation. And, well, what we do is the following. We take an edge in F1, so the codomain graph. Then I take the relation preimage of this edge, okay? And so I have some set over there, and I know that this set is finite by the condition number 3, all right? But I can now take the end of this edge, it's a vertex, and now I can take the relation preimage of this vertex. And if you remember, this must be a finite set of vertices. And now I take the target map. So I have here a bunch of paths, and I take the endpoints of these paths, and I map it to the preimage of this vertex. Well, by this compatibility of a relation with endpoints, I know that the image of this target map must be in the relation preimage of a target map of F. That's just the compatibility between relations and targets. But now I demanded that for every F, this map is bijective. Okay. It has a very nice interpretation in terms of pullback diagrams, but there is no time for it. Okay. Now I have a monotonicity condition, which remember I mentioned in the covariant setting, and I refused to explain it. So let me do it now here, bigger generality of relations. Yeah, this is the line where Elizabeth found the typo. So I'm very grateful that we corrected on time. So we say that our relation is monotone if the following happens. If I take two pairs in the relation, but what is special is that the right-hand side are edges, so f and f prime are edges, okay? And if it so happens that the path x precedes the path x prime, which simply means this notation here, which I forgot to define because I deleted so many slides. What happens here is x prime is bigger or equal than x, means by definition that x prime is a prolongation to the right of a path x. So in other words, x prime is equal x composed with some further path gamma, okay? So if it so happens that x prime extends x, and x is in relation with f, x prime is in relation in f prime, that's sorry guys, but you must have that f is equal to f prime and also x is equal to x prime. There's no other way, okay? That's the monotonicity. At the beginning, we got it slightly wrong. We wanted to have f and f prime not edges, and we wanted just to have an implication that if x is extended by x prime, then f must be extended by f prime, but then f and f primes are paths, not edges. And this turned out to be too strong. We found natural examples where this condition is violated and the star homomorphism still exists. Okay, this formulation seems to be optimal. Okay, and this is the toughest cookie. So I told you that the regularity condition in the covariant setting is honestly daunting. But maybe let me begin with this contravariant regularity. Contravariant regularity is very, very simple. If I have a graph homomorphism from E to F, okay, then basically I say that this is regular if the preimage, yeah, and it's called the right preimages, right? There's nothing wrong with writing preimage. Provided the preimage of regular vertices in F, well, this must be contained in regular vertices in E, okay? So in other words, the preimage of a regular vertex must be regular, okay? This is very, very important. Well, that means that your F cannot make a singular vertex regular. That's not allowed. If I give you a single vertex, which by definition, which Elizabeth introduced, means not regular, I cannot map it to a regular guy. That's not allowed. Okay. And this, if you take for your R, the map relation given by F, so you simply take as your relation the graph of F, okay? Then you can very quickly read out of this complicated blah, blah, blah that this is satisfied, okay? That's really quick and easy. But this daunting regularity condition that we have in the covariant setting, that this can be reproduced, but such relatively easy to parse condition 7, this was a brilliant idea of Gilles, and the proof is very difficult. Okay, but now let me explain to you what happens here. So for starters, we care only about the regular vertices. Okay, well, this is what second Kuntz-Krieger relation is all about. If it's not a regular vertex, forget Kuntz-Krieger, second Kuntz-Krieger. Okay. So for starters, we take a regular vertex V. Now, I take a relation preimage of this vertex V. So I know that I have a finite set of vertices, okay? Because R must be proper and because the relation preimage of a vertex is a vertex. It comes from an axiom. So whether you like it or not, U is another vertex. Okay? And now because I'm in paths, so you see, I use PE to designate the source map, but from the space of paths to the space of vertices, rather than from the space of edges to the space of vertices, okay? So here by X, I mean any path that originates at U. And here I would concur that it would be easier to write that let's take a path X such that it begins at U. This could have been clearer, okay? But here it is. So I take any path X which originates at any vertex U that is in the relation preimage of my regular vertex V. Aha. And when it happens, then I'm guaranteed that there exists X prime which is either a superpath of X or a subpath of X. And this X prime is in relation with an edge F that comes out of my regular vertex V. That's it. That's the regularity condition. So any path, right, that is emitted from any vertex that is in the relation primitive of regular vertex must have this property. This path itself need not be in any relation, okay? You can say, no, I'm not interested in being in relation. But it must have a superpath or a subpath that is in relation not with just anything, but with an edge emitted at V. And because V is regular, you know that it emits finitely many non-zero edges. Sorry, non-zero finitely many edges. This is the right syntax, sorry. Okay, so now please memorize all these 7 axioms. There will be a quiz at the end of my talk. And now let's reap off the benefits. Okay, so for starters, now that I gave you all these conditions, well, not only I have this obvious claim that this ambient category of relation morphisms subsumes both OG and PG op as subcategories. This is very trivial. So the first statement is very, very easy. And mind you, I have to put op here because when it comes to these path homomorphisms, when I include my path homomorphism as a relation, I do it by reversing arrows. Right? Remember, then this is the graph, but the function going from codomain to domain. Okay, so I have to put this up here. So that's completely trivial. But what is highly non-trivial is for starters to prove that when I take my relation morphism satisfying the 7 axioms which you just memorized, to prove that it's a category, this is highly non-trivial. It's really non-obvious that these conditions are composable. Okay. But okay, it is a category, and it's also not at all trivial to prove that these both categories, so this category of admissible, this is contravariantly regular target bijective proper ordinary graph homomorphisms, obviously, and the other one is regular monotonous injective and vertices path homomorphism of graphs. Yeah, we must have been really on high when inventing these names, but this is how it has been published. I cannot change it right now. Now we just call it admissible, and it's ARG, decent, honest, admissible relation graph morphisms, okay? Well, I mean, first we have to see that it's a category, and then we have to see that these 2 guys that we used earlier are subcategories. But we have it, we proved it. Better still, we have, oh, not yet, sorry, not yet, this is the next slide, sorry. Okay, at this moment, you can ask yourself the following inconvenient question. By defining this new category of relation graphs, I mean, these are new morphisms, right? I mean, the objects are the same, they are just any graphs. But by defining this new category, have we created a new universe? So we have something genuinely new? Or does everything boil down at the end of the day to what we had before? It's just a new packaging of things that normally were not packaged together. And the answer is we don't know. When it comes to being able to decompose a relation morphism into 2 map relations, by map relations, mind you, it was on my slide. If you want to sue me for not saying this, you cannot, because I said it. You see, we call them map relations. So I'm legally protected. Yeah, these are the definitions. This is what I mean by map relations, okay? So now the question is, can I decompose any graph relation into finitely many graph relations and map relations? The answer is I don't know. But what I know, well, first on the positive side, where is it? First on the positive side, when you make an assumption, which you already know from Elizabeth's talk, that you are row finite, so no infinidemeters, it's an annoying assumption because very many natural graphs are not row finite. My starting slide had a graph which was not row finite. Minimalization of compact operators is not row finite graph. Okay, so it's not an assumption that you are happy about, but it's not killing you, right? I mean, it's still there are many interesting graphs that are not row finite. All right, Cuntz algebras, right? So under this assumption of the codomain graph F being row finite, we can actually prove that any relation morphism is decomposable into map relation morphism like this, okay, RF and RG. And we have a counterexample in the sense that when F is not row finite, we explicitly construct a relation which we prove cannot be decomposed into such two steps. But then what's the next thing we do? We prove that we can decompose it into three steps. Okay. So we answered the question of decomposition into just two moves. Can be done always if your codomain is row finite. And if your codomain is row finite, you have an example where it cannot be done. But the question remains in full generality. Is it possible or is it not possible to decompose our relation morphism into finitely many map relations? And we don't even have a feeling of what the answer is. So we don't pose a conjecture because we honestly don't know which way it's going on. We don't even suspect what might be the truth. So I don't want to pose any conjecture because for me it's like flipping a coin. I have no idea. And this is a very difficult problem, believe me. And I don't see any immediate benefits of solving it. I don't believe anybody would get a Nobel Prize for solving this problem. And it's very difficult, so why bother? Yeah, I have. But it's conceptually an interesting problem, right? I mean, have I created a new universe? Do I have something generally new that was not there before? You know, when I define projective modules, I see, so there are modules that are projective but not free. Do I have relation morphisms that are just relation morphisms that cannot be decomposed? I don't know. But so far, for us, what is really most important is this one functor to rule them all, you see? So this is the take-home message. If you want to remember only one slide, please remember this one, okay? So to simplify the notation, and instead of writing this chi-p and equivalence classes, let me write SP to follow the sister algebraic native language. S is for isometry. By the way, I don't know why isometry is denoted by S. I mean, in most of the papers, S is an isometry. Okay, here these guys are partial isometries. Okay, to simplify the notation, I denote projections also by S. So when you have S with a vertex, it means the projection at this vertex. Okay, yeah, maybe symmetry. Yes, I don't know. And then when you have a path, well, it's completely obvious. The isometry is just multiplying out all isometries assigned to edges that compose into the path, and you multiply in the same order. Okay, so this is our notation. And now, as I said, the following theorem generalizes previous functors that we had, but one was covariant, one was contravariant. All right. And we chose the contravariant direction because I wanted to be aligned with the Gelfand-Naimark theorem. Right, but the functor that assigns to compact Hausdorff spaces unit or commutative sister algebras, this is a contravariant functor, turning pushouts to pullbacks. Okay, so that's the same thing I want for our functor to be contravariant and to turn pushouts of graphs into pullbacks of graph sister algebras. And when you look at this formula, well, that's very simple. It suffices to give it on generators, which are edges or vertices. And with my uniform notation, I can just write one formula. So basically, take the relation pre-image of your edge or your vertex. Okay. If Q is a vertex, then you know that P's are vertices, so then you just have a sum of projections. But if your Q is an edge, well, then these are any paths. They can be vertices, they can be paths of length 1 million. The only thing you know that it's finite, because remember, we have this properness here, right? So the finite sum of partial isometries / projections, which are there, right? And this defines a contravariant functor from the category of admissible relation graphs to the category of sister algebras and star homomorphisms. Mind you that here, there's a certain subtlety. Yeah, maybe, oops, I have only 1 minute to finish. No, it's okay. I will not say it. Let me skip it, even though it's interesting and it's hard for me to refrain from this. Okay, but I will be a good boy. Okay, so this is precisely the main theorem I want you to bear in mind. We have this one functor, which is defined on the ambient category, encompassing the previous categories that we used for our covariant functors. And if I restrict this functor to these subcategories, I recover the previous functors, both covariant and contravariant. Okay. So that is the upshot. So this solves the problems I alluded to at the beginning, right? First, I applied just one functor to a commutative diagram to have a pullback theorem. It's no longer a mixed pullback theorem because I have just one functor. And also, when I have to combine simultaneously covariant and contravariant homomorphisms, homomorphisms use covariant and contravariantly. Now I can put it into one relation and just have one morphism between graphs. And this is exactly what I want to exemplify. At a certain moment, we bumped into an interesting problem. Quite incidentally, while being in Arizona visiting Jack Spielberg, we saw how to embed the Cuntz algebra O2 into, 2x2 matrices over the Cuntz algebra O3. It was completely incidental, right? We were working on our locally derived graph construction, and we had the Cuntz graph. Then we constructed the locally derived graph, and by our theory, we had a graph homomorphism going there, so it used a star homomorphism going there, but we didn't quite know what the sister algebra was. But you have a certain classification theorem, so when Jack Spielberg saw it, he said, wait a second, he immediately computed K-theory and the class of 1 in K-theory, and by classification, he knew it was M2 or 3. So he got very excited about it because people typically, a typical embedding of Cuntz algebras is OM in ON, but with M bigger or equal than N. Plus congruence relation, which has to be satisfied, otherwise it doesn't work. Okay. And all of a sudden, somehow you embed smaller Cuntz algebra in the bigger Cuntz algebra, but amplifying it by matrices. So it was something interesting. So then I asked myself the obvious question. So what can I do? Can I include ON in some MK OM? If this congruence relation is satisfied, K-theory allows it. So by a well-known theorem, if K-theory allows it, then such a morphism exists. So we knew such embedding exists, and we wanted to find them explicitly. Okay. So this was our problem to solve. And if you look at the top graph, that's exactly the Hawaiian earring or rose petal graph, which gives you the Cuntz algebra ON. And this is relatively easy to prove that, okay, if you want to have not just the Cuntz algebra OM, but you want it to be amplified by matrices, basically what you do, you blow up your base point into the path of length K minus 1 if you want to have K size matrices. So if you have K vertices, then you have matrix of size K, right? So 2x2 matrices are just given by blowing your point into an edge. And this is a high school exercise to prove that the graph sister algebra here is just matrices over Cuntz. That's immediate. It's like almost canonical, right? But we didn't know how on earth to relate this Hawaiian earring graph with that graph so that we could induce a nice star homomorphism and by functoriality have embedding of Cuntz algebras in matrices over Cuntz algebras. Okay. And then one night I dreamed about this graph. And this graph solved our problem. Because on one hand side, there is an obvious way to collapse this graph to ON. I didn't define in full detail of what are these axioms of target bijectivity and so on and so forth. But okay, properness is obvious because the graphs are finite. Regularity is obvious because all vertices are regular. So for image of regular being regular, it's trivially satisfied because everything is regular. So the only subtlety is target bijectivity. Okay. And in a nutshell, what target bijectivity tells you is that I can identify only if I want to identify different edges, that they have to have different endpoints. And I have to identify as many different endpoints as I have edges. So here it works. I can do it because you see, if you look at these red arrows, in fact, they are sets of n-1 arrows. Okay. So what I do, I pick up one arrow out of each red set. So I have k of them, all right? And I also have k vertices. So as you see, I identify k vertices, which are endpoints, and I identify k arrows, each of them ending in a different vertex. So target bijectivity is satisfied. I repeated n-1 many times. Again, everything is satisfied. And the last step, so at this moment, what I did, it's k times n-1. Okay, that's what I did. But I still have one missing. And this last loop missing is exactly, you identify all these black arrows into the final loop. And you, of course, identify all vertices. So target bijectivity is satisfied. So I have a graph homomorphism from fmnk to en. So by the contravariant factoriality, I have a star homomorphism from here to there. And now I somehow still wanted to see that these are matrices of Cuntz. And here shift moves come into play. Because you see, if you remember of what Elizabeth was explaining, what she allows us to do, she says, okay, instead of having an edge ending in here, I can basically shift it to ending there. So what I'm doing, I'm simply shifting all these edges all the way to end over there. So here I have n-1 edges ending in vk, n-1 edges ending in vk-1, blah, 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 up to here, n-1 edges ending in v2. But this is wrong because here there are only black edges which end at these vertices, okay? The red edges should go all in here. But if you think about the shift move exactly as Elizabeth defined it, then you can shift these edges to end in there. These are exactly shift moves, and it gives you an isomorphism of graph sister algebras. And from our perspective of, this is what I explained in my sort of after talk, like afterburner and after talk, what happens there is that I take an edge which ends at the wrong vertex and I map it. I cannot map it into an edge because there is no good edge here. So I map it into one of these red edges going to V1, but I follow it by an edge going to the vertex I want. And if it's a vertex, if it's an edge which ends further down, well, then I have a path which goes further down. Yeah. But this would be like iterating of the shift moves. Okay. And for us, it's a path homomorphism of graphs. It satisfies all the axioms. Regularity is satisfied here very easily because when I prolong my paths, I can do it in a unique way. This is where regularity becomes subtle if it's non-unique, okay? That's why shift moves are more interesting than these examples. They properly generalize it. So this is why I'm very happy about it. But here I can very easily convince yourself that this is regular. And what else? You're obviously injective on vertices because your identity on vertices. And finally, monotonicity is also obvious because each time you begin with a different edge. So no path that you have is a prolongation of another one because the first edge is always different. So the first part of the implication is always vacuous because it's never satisfied. So the implication is always satisfied. So that's it's an admissible path homomorphism of graphs. So this induces covariantly. Okay. So here I go from the middle up, but I induce contravariantly a star homomorphism. Then I go from the middle down, but I induce covariantly a star homomorphism. I can compose star homomorphisms. Okay. And when I do it, well, this is exactly what I do. I go left and I go right. I have this congruence relation satisfied as demanded by K-theory. And then I combine the two into a star homomorphism that embeds On into MK of On. And thus I satisfy the goal, which I invoked at the beginning of my talk on my second slide, that I want to have a nice category of graphs, so that by contravariant induction, I can induce, I can turn graph homomorphisms, some morphisms of graphs into star homomorphisms of graph sister algebras. And I want to have, as part of this framework, some interesting examples, not something very simple, but it's kind of not reverse engineering. Well, we have a problem. We know that such a star homomorphism exists. We believe it's given combinatorially. So now we found combinatorics behind it. But to find this combinatorics behind it, we needed a common denominator. We needed to combine both covariant and contravariant factoriality that we had before, but it's much better to talk about one category and one functor to rule them all. And I better shut up right now. Thank you very much for your patience.
You are doing this on in C
Mhm.
language. Can you do it for living?
Yeah, of course.
All of this.
Yeah.
So that O2 sits inside into O3. You can do it for L2.
I believe so. Yes. Yes. No, I mean, okay, let me put it this way. Of course, I can do it. When I say I believe so, I'm not sure about classification in theorems. For instance, I use honestly C-star algebras to know that if K theory allows a star homomorphism, that it exists. I have no idea if it works for Leavitt path algebra, such an implication. But of course, the moment I construct the star homomorphism from graph C-star algebras, because it's given combinatorially, you see, another beauty is that these are polynomial formulas. Because when you look at the covariant factoriality, there are no sums. But you can map your edge into a path, which means that you can map x into y to the power 100. So you work with monomials, but the monomials have different powers. It's no longer power 1. When you look at the contravariant factoriality, you preserve the grading, you preserve the gauge action, so you cannot change the length. So you map your edge into the sum of edges or your vertex into a sum of vertices, okay, but there are no powers. But when you combine the two, what happens? You have sums and you have powers, which means you have polynomials. But still, these are polynomials. So we give you polynomial formulas on embedding of these simple C-star algebras over there. I mean, these are hard cookies because they are not pliable, they are not flexible. These are very rigid C-star algebras.
We hear that you have this map going from O and M.
Yeah.
It injects.
Yes, it must inject. Because ON is simple.
So that part doesn't come from the relation between the relations with these admissible relations.
It comes, of course.
It comes from there. So if I give you an admissible relation, can you tell me immediately if on the level of C-star algebras it's injective?
No.
That you cannot.
No. We have a certain. Of course, we can try. One can try to investigate it. What would be the sufficient, or better still, sufficient and necessary condition for a relation to induce an injection, surjection, or bijection? That's something to be worked out. We remember we just submitted the paper.
So here, injectivity becomes because
I know that ON is simple, right?
That's it.
But, however, having said that, when it comes to contravariant factoriality, so to graph homomorphism inducing equivalent star homomorphism of graph C-star algebras, we know that if our graph homomorphism is surjective, then the induced star homomorphism is injective. And also, if our graph homomorphism is injective, like a subgraph, then we do star homomorphism is surjective. This we know, but we don't know it the other way around. I mean, the other way around was blatantly false. Yeah. So you need not be surjective on graphs, and you can still be injective on graph C-star algebras. The Cuntz example is a good example where it fails. So it's not like with Gelfand-Naimark, because over there it's complete equivalence. You are injective on compact Hausdorff spaces if and only if you are surjective on C-star algebras, and the same, you are injective on C-star algebras if and only if you are injective on compact Hausdorff spaces. It doesn't work for graphs. The implication is only one way. If it works for graphs, then you just turn injective into surjective, surjective into injective, and it works for Leavitt path algebras or graph C-star algebras.
One question. So in Arizona, you realized that O2 sits in here.
Mm-hmm.
There is an explicit map. You found explicit
yes.
map. Okay. Now with this here, you know also exactly how it sits. I mean, this map between the graphs gives you that explicit map.
Actually, we didn't have explicit map back then. We just knew that we had it, oh no, sorry, I'm lying. No, we had an explicit map because this is the collapse of a locally derived graph to its initial graph. Sorry, yeah, we had an explicit map. Sorry.
And that now you've recovered that explicit map.
Yes, exactly. Yes. But this was a special case. Things are much easier when the difference between K and M is 1. When we tried to do it in full generality, it was a bit of a tough cookie. This is why we needed this third diagram.
That's M minus N K.
Yeah.
That's
Yeah. That. Sorry, I said it incorrectly. What the difference between this and that is 1, it's easy. But we couldn't, because for starters, we thought that, okay, all these embeddings are given by locally derived graph construction, but it's not. We couldn't figure it out. So I really had to have this middle graph to have explicit formulas. Yeah, and I was wondering, yeah, so this is what I refrained from saying during my talk, but I will not refrain from saying it now. Namely, when it goes to this contravariant induction, this you see when you are in here, right? Then you are gauge equivariant, okay? And on the top, if your sister algebras or Levi-Pav algebras are unital, then your homomorphisms are unital. When you go into the covariant induction, not only you completely screw up gauge action or grading, but also even if your Levi-Pav algebras or a graph sister algebras are unital, it is not true that these homomorphisms are unital. And a typical example is embedding matrices in bigger matrices. As everybody knows, there's no unital embedding, but the way you construct compact operators or M-infinity matrices in the Leavitt world is that you have this non-unital embedding. So I have unital algebras, and I have an algebra homomorphism, which is not unital. So this is also recovered by this covariant functoriality. So here you lose both. You lose equivariance and you use unitality, even if your algebras are unital. So that was a remark I wanted to make.
Provide this all in the language of the IMPAN algebra. If I just say that everything you have done, this morphism on the level of algebras, or a star isomorphism, they're not done because you can just fix that stuff.
Exactly. Yes.
So if I just do it on the IMPAN, everything just and is it correct?
And this is the way we do it. In fact, I mean, we do it for Leavitt, and then then we just star it. Yes. Yeah, but it works for Leavitt. I mean, all our theorems are for Leavitt. And in fact, right now we are working, in addition to this extended graph homomorphism, which I mentioned on my afterbird talk, we also want to have a pullback theorem for this big new category. And we kind of have it, but what we are unhappy about that it's just for Leavitt so far, because it digs so deeply into the structure that we have the desired lemmas at the level of Leavitt, but we are not sure about the Leavitt of graph sister algebras, which makes us very frustrated. But I hope we will resolve it. Okay. So, one of our motivations of studying morphisms is to turn diagrams of graphs, which are easy to grasp, they are combinatorial, into pullbacks of sister algebras that have consequences in K-theory, in CW complex structures, whatnot, things that you really study, okay? And we have two pullback theorems. One is just push-out to pullback theorem for the contravariant functor. We have a push-out graph with many conditions of graphs in the category of graphs. We apply our contravariant functor, and under many conditions where troublemakers are typically breaking vertices. So here I agree with Elizabeth. You can be scared of infinite emitters. Infinite emitters are really troublemakers, okay? But it's also what makes this fight difficult. I mean, we have a worthy opponent to fight with, okay? So under many conditions that have to be taken care of when you have infinite emitters and breaking vertices. I mean, it's just not infinite emitters. When you have breaking vertices, this is a problem. But we still have a push-out to pullback theorem in very big generality, okay? Now we also have this mixed pullback theorem, which was explained by my first diagrams, okay? And now we want to have a theorem, a pullback theorem that would unite these two pullback theorems. And we almost have it. We have it at the level of Leavitt-Pav algebras, but not graph sister algebras. The reason being that if I take a pullback of dense subalgebras, okay? I have a pullback. And here I have a pullback algebra. if I complete this algebra here, this is not the same in general as completing these 3 algebras here. Yeah, they are dense, so you can, this is all done in a unique fashion, right? And then I take a pullback here of a completed algebras, then in general they are different algebras. The reason being that when it comes to pullback, polynomials suck. I mean, imagine that you take 2 circles and you intersect them over an arc, so it's more than 1 point. If you identify 2 Laurent polynomials over infinitely many points, they are equal. So when you take the pullback of Laurent polynomials, you just get 1 Laurent polynomial ring. But when I go to continuous functions over the circle, I take the pullback, I have continuous functions over letter 8. It's a completely different animal. Okay? So pullbacks and completions do not commute. So we cannot say that we have a pullback theorem for Leavitt, we have a pullback theorem for graph system algebras. Okay? So this is what we are sweating on. So far we managed to somehow put a common denominator, at least for the earlier versions of our pullback theorems. So both pullback theorems, at least in some special versions, a special case of our pullback theorem for the relation morphism category, okay, which for me is a miracle. It's amazing that it works, but it's only Leavitt. And we don't want Leavitt, we want graph system algebras.
Questions or comments? In that case, let's thank Piotr.
Oh, there is on Zoom. Sir, on the first slide, you told that quantum graph, generalized graph system algebras. Can you suggest me some reference? Well, okay, not during the talk. And anyway, this was done a long time ago. First, let me stop recording.